Okay. Good evening, everyone. So today we will start our discussion on week 8 content. So firstly, we'll go through the concepts of week 8, followed by some question and answer, and then we'll address your doubts if any. You can find the slides and the video recording for this lecture in the links. So the first module was for the optimal placement of pressure measurement units, that is PMUs. So first we'll look into why we require these PMUs in our system. So firstly, for real-time monitoring, we saw this in the previous lectures as well. So since they provide with the real-time measurements of voltage and current pressures at various locations in the grid, and using these measurements we can know the state or health of the grid. So they facilitate the real-time monitoring of our power grid, and they also help for wide area situational awareness. That means since they are deployed over a wide geographical region, and then in the control center we have situational awareness tools such as we may have large screens where we have the physical like outlay of the grid, and let's say whenever the system is going to a critical state, then they may observe some red kind of marks at those locations indicating that we need to take some control actions in those areas. So that visualization or situational awareness we can have due to this PMUs, like this voltage stability, frequency deviations or oscillations. So these we can monitor in the control center utilizing the data from the pressure measurement units. And we have also seen that these data from the PMUs over the region, they are synchronized with the global position system or clock, so that we have a time synchronized data with us. So since we'll have a synchronized data, this will help us to compute or know the actual phase angles and their difference at each time instant. And then using these phase angles and phase magnitudes, we can calculate other quantities such as power flows, line losses, frequencies, and this will help the system operator to monitor the health of the grid, and hence enhance, we can say, the grid stability. Also, so these measurements that we get from the PMUs, they will give us the data for various power system analysis, such as we have seen previously for state estimation, for contingency analysis, for transient studies. So once we have these phasors, we can go for other power system studies to monitor the grid. And obviously, this will also help the integration of renewable energy resources in the grid, because using this PMUs, we can handle the intermittencies of these renewable sources, and hence this way the PMU will support the integration of the renewable energy resources. And it will also help in grid resiliency, because once we are monitoring the grid in real time, we can avoid, we can say, various contingencies or outages in the system. And also, if certain outages take place, we can quickly revive the system, because using this data from the real time, we can quickly isolate the faulty section and we can ensure continued power supply to the healthy section. So that way, it will help in the resiliency, because when the system is more aware of the system, it can take better, we can say, informed decisions to handle those contingencies or outages. So what are the challenges with this PMU installation? So will anyone like to speak? What are the challenges that we are facing for installing these devices in the power system? Anyone? Like, why don't we have this PMUs? We can't install at every location in the grid. That way.
Uh, Due to remote sites, those are on the remote sites, we can't provide any internet connectivity or any links to
Yeah,
the.
communication requirements, those remote locations
Yes.
that won't have. Right, you're right.
Yes.
Any other points? Anyone? Okay,
Uh,
so,
like,
uh,
who will be responsible for installing these kind of devices? Either utilities or the grid grid controller of India. Who will be responsible for installing these
so
services?
these devices, they are a part of, we can say, grid automation. So that will be carried out by the government only in a phased manner to like improve the substation or the grid. So it comes under that schema. But we have also like government from Grid Control of India only. So they have assigned plans like how PMU installation basically they carry in phases. Like in first stage they will install at some locations, and then after those task has been completed, they will have second stage deployment. So likewise,
Okay, okay.
his first one was the budget constraint because these are we know costly devices. So installing this at each and every location can be expensive. Plus, we don't need these devices at each and every location. We'll see it in the next slides. Like why installing the PMUs at certain location is also enough for carrying our or monitoring of the system. So if we install at every location, it will be basically we can say mismanagement or misutilization of the resources. And then infrastructure, as Sashidhar sir has pointed out. So not only installing these devices, once we install these devices, we need to have communication infrastructure. We need to provide with them Wi-Fi's and all those things, and this will again add up to the cost. So in the remote areas, this communication infrastructure may not be available. So hence, it will also be a barrier for the installation of these devices. Then additionally, we'll also require sensors like we'll require voltage transformers, current transformers, and this will also add to the cost. Then data handling and storage cost. So we know that these PMUs they will provide us with high resolution data at very high frequency. So we need data management centers or data control centers who can handle to process this process and as well as to store this amount of data, because we had already seen that we store these historical data to carry out various power system studies. Like this historical data may be useful for carrying out generation expansion planning or transmission expansion planning, or this reactive power support planning, load forecasting. So this data is important for us, for which we store this historical data. So this is one thing, and also we need to process this high frequency data at the real time for the real time monitoring. So we need the historical as well as the real time monitoring. So this will add on for the data handling and as well as data storage cost. So what we do is we do a trade off between the cost and the coverage. Basically, for as I had said in the first point, we don't require the PMUs at each location for the monitoring of the grid. Only installing them at some of the locations will also be useful for monitoring the whole power system. Like for only in suitable locations, if you place this devices, you can monitor the whole power system. That is known as observability basically. So this will help to stay in our budget constraints while we do not compromise on the observability of the system. So
Excuse
basically,
me, ma'am.
hmm.
Do you have any PMU data? What kind of data is capturing? Like how it will be there?
This we had seen in the lecture of protection. If you remember, for DFT and DTF, half cycle DFT, we were computing. So those kind of data on.
Oh, okay, okay, ma'am.
Okay.
And one thing, ma'am.
Huh.
See, even these PCUs and with this relays, every time the data will be going to the NRLDC, they are monitoring everything.
Huh.
But apart from that, why they require PMU? The same data what PM is giving to them, the
Hmm.
same is being generating from the BCU. We can see the voltage level and current, how
They
much
are
it is
getting
flowing in
from
this line.
what? Sorry, I can't. They will get this data through the sensors to the PMU only. The load dispatch center will get the data. No. So what you were saying?
Uh, like we are linked up with the each and every data will be going to the NLDC.
Huh.
Whatever the power flow here we are having,
Huh.
voltage status and status, everything will be seen. And apart from that, why extra this PMU is needed? What whichever the
So
data is
how
being
this data will NLDC is getting from the PMU data,
through
right? In the real time.
no, not okay through PMU also, but uh, from they can get the status of everything, ma'am.
But how?
If lines are,
But
they
they
are
can do
having
the
the computation.
computation. No, see, what I get from you is you are saying that since they are the dispatch centers, they have the data for the maybe generator dispatch PG they are having, and they know the PDs also. So from that, they may compute the voltages and power flows in the lines. But that is in the pen paper on the software. But what is happening in the real location? How will the NLDC get to know that the load has been changed or some line has been cut off in the real time? And also, when we are computing this in the computer software, so several physical you can say the line power flow limit or the line parameters R and X, they are also weather dependent parameters, they are also changing. So those characteristics are very difficult to model. So ideally what we take is resistance and reactance are constant, and we are doing our power system studies. But in the actual, what may happen, let's say if you go to Jammu Kashmir region or something where we are having extreme low temperatures and high temperatures, this R and X will be different from what they have on the paper. So this mismatch will happen. So in order to, we have on pen and paper the values of voltages, but that may not be necessarily there that it will match with what is in the actual location.
Uh,
So are you trying to say the same thing, or in like I
no,
was not sure like how they will have the data.
through communication line link itself, we will send the data to them. Each they will be having the status of our each isolators, breakers, and whether the line is tripped or not. Even current flow, how much it is flowing, power flow, how much we are is flowing. They will be getting every data to them through the communication link. We have
Okay,
two communication link redundancy too. Um,
okay.
uh, uh, Apart from that, again, but with PMU, why they require this same kind of data? Even though if they are having a voltage level current.
Uh, so you're saying that like each substation, they will be having their own meters, and they communicate those data to the.
area, but PMU cover is more. PMU covers more area monitoring as well as time synchronization is very important for data analysis.
Are you saying something? Sashidhar sir. Okay, are you there? Would you like to say something? We were having a discussion.
Ma'am, to continue, please continue.
Okay, okay, we'll then continue. So, okay, we were like, what were the challenges for this installation? So, firstly, is whenever we are having this budget limits and the grid operators, they will prioritize the installation of these devices at the critical locations only, like critical substations or critical generation location. So first, like when they are planning to do it in phase wise, so in phase one they will install these devices at the locations which are very much important to us, very much crucial for the power system. So that way we can carry the phased deployment of this device. So basically this phase deployment. So in the first like stage, we can go for the most critical ones, which are very, very important. And after this stage has been completed, then we'll go for the second stage, where the next hierarchy important devices, important location, these devices will be installed. So that way we can combat this economic challenge that we are facing for installing these devices. So in the right, you may see this is the map of India, where we are having this red dots as the pilot projects that are being carried out, and the white dots are the PMUs that are set up by the IPPs or independent power producers. Then we have PDCs, star mark, star ones, black star ones. These are the local PDCs, and then we have the white star, which is the regional PDC, and then we have the central PDC here at the New Delhi. So this is the, then we'll move to the mathematical model of this. So firstly, uh, can we, can anyone like say like this orange box is the optimization problem for the placement of the PMUs. So why from this we are getting the output as the location for the PMUs. Then why are we carrying this DCOPF? Why this is necessary to carry out this? So basically you can see the orange one. So here we have the cost minimization. Basically this will be our objective. This is our objective, and these are our constraints. Together they are forming the optimization problem for the optimal placement of PMUs. So this is what we'll get after running this optimization problem. We'll get the optimal location of the PMUs. Then why are we carrying this DCOPF or OPF calculations also? Because our aim is to get the location. So I'll first maybe we'll discuss. So each we can say optimization problem, it will have a objective function. So the objective function is the goal that we want to achieve. So where here it was cost minimization. So can anyone tell me what other objectives can we have in the power system except for cost minimization? What other goals we can have in general? Anyone? Like what do we want? Firstly, let's say we want to operate at minimum cost. Next, What about losses in the system? Do we want to minimize it or maximize it? Anyone? What about losses in the system?
Minimize.
Yeah,
Minimize.
yes, sir. So losses, obviously, these are not useful for us because we can't convert them to utilize them basically. So losses we will try to minimize. Then any other objective in the context of emissions or pollution, what can we do for emission? Yeah, so emissions like greenhouse gases, we'd like to minimize this. Then any other? Think from the perspective of private players. So what do they want? Any private entity, what will be their motive?
Maximize their profit.
True. So, rightly said. So apart from government, if any private player or any entity is there, it will always try to maximize its profit. And any other? So these are, we can say, some of the examples of objective function that we can have in the context of power system. And then coming on to constraints. So constraints are of two types, of equality type and inequality type, right? So can anyone tell me some examples of this equality and inequality type constraints in power system? Equality constraint.
Is always equality.
Sorry, sir. Can you repeat once again?
Load. Always a load.
Load. What should we do? Load. Actually, your
All
voice.
we
Yeah.
have to match the demand load. So generation is equal to demand is the equivalent strength.
True. So generation. So sum of the generators from generation from the generators should be the total load that is being served, plus sometimes if you consider the loss also, if you are considering, but sometimes you also neglect this. So this will be our equality constraint for power system. Then what can we have for inequality constraint? Anyone?
See band limit
Which limits are
like frequency 49 point.
actually I think you are having poor connection. So frequency I could get one. Okay. So any so basically actually I'm not getting any voice from your side. If you can also type in the chat box. So what frequency is there. So since frequency is not always directly coming in the, you can see, power flow equations or anywhere. So this frequency is related, we can say, to the angles, right? Delta. So since these deltas we have in the power flow equations, so we in turn what we do, we impose the limits on this delta, and this delta will in turn ensure that the frequency is in limit. So we can say that delta is within limit minimum and maximum, where then we have this generators, they'll be also having their limit. So they will always produce non-negative power. So we can say this generation limit will be there. Then what about transmission lines? They will be also having certain limit, and we know this line power can flow from both the directions, right? I to j or j to I. So this line limit, it will be, let's say its maximum capacity is S. So if you consider in this direction, so the minimum power flow will be negative times, because it will can also flow in this. So basically S I j, and maximum power flow that can flow from I to j is S max. So these are some examples of the inequality constraints. And so these are some of the inequality constraints for the power system. So what we mean by this, if we consider, let's say, an objective, basically what we have, let's say we have a two variable optimization problem, right? Let's say the variables are x and y. So let's say these are my x and y axis, and I have these two variables to optimize, let's say. So what we mean by these constraints is we are limiting this search space. If there is no constraint, that means x can take any value, y can take any value, and only we'll have the objective. So can anyone tell, if we don't have any constraints, then what will be this objective function value?
Right.
Infinite, true. If you don't have any constraint, for maximization problem it will run towards infinity, for minimization problem it will run towards minus infinity. But if you are having constraints, so what we'll do is we are limiting the feasible area or the search space. So basically when I impose a constraint, let's say on the limit of x, I say, let's say that x is limited between 0 to some value, let's say x max. So what I'm doing, let's say x max is positive here. So I am saying that x can be any value between 0 to x max. So can anyone tell, like, what will be the feasible area for this? If we consider this constraint 1, so in this area x is negative. So this is no longer our feasible area. because we have limited x between 0 to x max, and also in this area x is greater than x max, which cannot happen. So these areas are also not feasible. So let's say we have only this constraint. Then let's say I have a constraint that x plus, or let's say I have x equal to y constraint. So what will be this constraint basically? This is the equation for straight line, right? So what I'll do, so basically x equal to y means we'll have a straight slope, right? So I'll not go beyond this because this is not our feasible set, but I can't go also this way. So basically now I am saying that my solution has to lie on this line only. So after this constraint, again this region is also taken out. This region is taken out, this region is taken out. So finally what we are having? We are having this straight line. So our solution must lie on this particular straight line to satisfy this constraint, and this x value, it can be go up to x max only. From here, let's say my objective is maximize x. So if my objective is like this, can anyone tell me from here what will be the value? You see x is starting from 0 and increasing going up to here, right? So what is the maximum value of x possible basically? That is x max only. So the optimal point or the optimal solution is basically this point, only one point. This point is our solution. So our optimal x star, I can say, is x max. And what about optimal y star? That will be also equal to x star, x max basically, because we have taken the constraint x equal to y. So this is my final solution considering a problem with this objective function and this equality constraint and this inequality constraint. Basically this is the objective with two constraints, then we get this as the solution. So this is the brief overview, like how we are carrying out this process. So for the PMU problem, we'll see it in the next slide. Okay, economic dispatch versus OPF. So anyone can tell me what is the difference between these two studies? Economic dispatch versus optimal power flow. So economic dispatch, what we do, what was our objective here? Anyone? So for economic dispatch, we always have our objective as minimization of cost. Minimize the cost of generation basically. So we have the generation cost, let's say C as a function of P, as we generally take commodity cost. So basically AI times PI square plus BI times PI plus CI, for I is here generators. So what we'll do here, we'll minimize the cost of generators. So basically for I equal to 1 to all generators in the system, we try to minimize the summation of their cost functions. But contradictory to it, what the objective of OPF can be anything according to what study you want to carry out. So it can be maximize profit, maximize the amount of load to be served, maximize load, minimize loss. So depending upon what study you are doing, the objective can be anything here, but for economic dispatch, the objective is always to minimize our cost function. Then moving to constraint, we have only one constraint here, which is to the limit on the generators. Basically, this PGI should lie between the maximum generators for all generators. And we have that the summation of PGI should be equal to the total load. So this is the economic dispatch. On OPF, we have same this constraint also here, generator limits. We have this power balance. In addition to this, we have another important constraint. Can anyone guess what it is? Anyone? So here, in addition to this constraint, we'll also have the constraint on the delta min max, the voltage min max, that is, it should be between 0.9 to 1.1 per unit, and we have also the limit on the line power flow, S line. So this is a basic OPF. In addition to this, you can also have other constraints depending upon your problem. You can have other additional constraints also. So for our study here, we are taking a direct current DC OPF based formulations. So here DC means we are considering that V is always 1.0 per unit. So we only have delta here. You can see here we have only the deltas, right? So here our objective is minimizing this operating cost of the generators, and the constraint is, you can see here, this is the power balance equation basically. So delta I minus delta J. So if you like this quantity will represent, can anyone say what is this? Delta I minus delta J upon Xij, where Xij is the reactance of the line Ij. So if you compute this, what it will give, anyone? Basically, this will give the power flowing, no? Pij in the line connected between bus I and bus J. The power flowing will be Pij, which is given by delta I, that is voltage angle at this bus, delta J, voltage angle at this bus, and divided by the reactance of the line. So summation, so this Pgi minus Pdi is basically the injected power, right? Power injected. So what should be the power injected? Should be equal to the power that is flowing out, right? This is the KCL equation. Input power, incoming power should be outgoing. So basically, if this is the line I with bus ij, so if this is the P injected, this P injected should be equal to, let's say I have another bus K here. So what should be P injected equal to? It should be injected will be summation of outgoing. So Pij plus Pik. So I have this is clear. This first equation, first equality constraint basically. Then we have this line flow limit. Basically, this is the power flowing between line I and J, and it is between line. It should lie between its maximum and minimum limits. And basically, then we have the limits on the injected or generated current, basically PG. This will be for the generators. So, and PG minimum is usually 0, or it can be greater than 0, but it can never be 0, like less than 0. It can be 0 or any value greater than 0. So this is our DCOPF problem. And can anyone tell me what is the solution for this problem? Like what will get after solving this optimization problem? Or basically I'm asking what are the variables here? We are optimizing this problem with respect to which variables? Anyone? So this is the objective function, right?
PIs.
PIG basically. PI generated, right? Demand is known beforehand, and we'll also get the delta is, and from this delta I again we can compute the Pij also. So this is the result that we'll get. Basically we can say these are the independent variables, and Pij is the dependent variable because it will be a function of the delta. So this is a dependent variable. These are my independent variables. So after solving this problem, we'll get the optimal values for these variables. So then we have this optimal PMU placement problem considering the solution of the DCOPF. So how we are incorporating the solution of the DCOPF, we'll see here. So here it is a cost minimization problem. So this is CPMU cost. X is the binary variable representing that if you have a PMU present or absent. So basically if this binary one is there, then you'll have the cost CPMU of the installation. If the PMU is 0, then you'll have most. If the PMU is absent, basically then X will be 0 for that bus. Basically the cost will be 0. So that way we are minimizing the cost of installation considering this state estimation constraints. So why are we going for this state estimation and observability constraints? Anyone? Why are we considering this?
Because now our problem is digital. State estimation is essential.
Digital, so like what? So why particularly these observability constraints need to be considered? Why not any other constraint? So basically we have what we are doing is we have, let's say, 9 bus system. So what we are trying to do is we are trying to find the locations of the PMU for this 9 buses, such that if the PMU is present at, let's say, bus 5, then what measurements we will be having? We will be obviously having, considering that we are considering the DC solutions, we will be having delta 5. So the objective is, using this delta 5, the whole system should be observable. That means using delta 5, you must be able to compute the state of all other buses in the system, from delta 4, delta 3, delta 2, delta 1, delta 6, like delta 7, delta 8, and delta 9. So if using only delta 5 we can compute the values of all these states, then we can say the system is observable. But if using delta 5, the system, the state of all this all you cannot compute. So basically our motive is not being fulfilled. No, we want the real-time monitoring of the large location. So this is basically, we are trying to find that how many PMUs we need to install in an area, so that from those points we'll get the most accurate one, the measurements basically, or the true values. From these true values we'll compute the state of the system for all other buses. So if you can do that, then the system will be observable. Otherwise, if it is not, then our motive is only not being fulfilled. If say you get the answer as 1 PMU you install, but you cannot get the values of deltas at other buses, then it is equivalent that you don't have a PMU in the system, because you can't monitor the whole system, right? So hence we want to obviously minimize this PMU to be installed, but we have, using those minimum number of PMUs, we must be also calculate the system states at the all other buses. So is this clear? So without this constraint, what would happen is, it will always give the minimum number is 0 we have, no? It will tell don't install at any bus. So this will only, like this, imposing this constraint, observability constraint is important. So that obviously minimum number, but using that minimum number your goal should be achieved. And your goal is to find the state of the system at all buses. So for that, this observability constraint is important. And then we have the state estimation constraint. So this PGI true is what you are getting from the DCOPF solution, right? PGI true, then delta I true. So all these true values we are getting from the DCOPF solution. And what you are trying to do is, you are trying to minimize the error basically between the true and delta I is computed using this formula. So you want minimum error which is less than epsilon. So basically, if let's say for this equation, if x is 0, then what will be this constraint reduced to? basically x is 0, so this part is 0. X is 0, then it will be 1. Basically you get Pg minimum less than equal to Pg less than equal to, if x is 0 here, so you get Pg maximum, and this term it will go to 0, right? Similarly, if x equal to 1, what will be the value? If x is 1 now, so you will get this, which is, I will say Pg true 1 minus epsilon, plus if this is now 1, so it will be 1 minus 1 0, so this term will be 0, less than equal to Pg less than equal to, this is 1, so this will be 0, this is 1, this will be Pg2 into 1 plus epsilon. Basically, if you have a PMU, then the Pg should be lying between the actual value that you get from the DCOPF with some tolerance limit we are having. And if x is not, if basically x is not there, means PMU is not there, so the constraint will be reduced to a normal constraint because you don't have the true value here. So I hope this is clear. So considering these all equations, we'll get the optimal locations of the PMU, basically x stars from x1 to x9 star, for if we are considering a 9 bus system. So it can be like some 1, some zeros. So likewise you'll get the solution. So how this observability is like, if you know one value of voltage and current phasors, and subsequently how you can compute other values. So let's say I have this ij. So if I know the value of vi, let's say this is a complex, so I'm representing by bar. So can you calculate vj bar? Let's say the impedance is z here. Anyone? Basically vj will be vi minus the drop, right? So what will be the drop? What will be the voltage drop in this line? It will be iz, right? So it will be iz. Then once you know this, so this is the first point. Basically, if you know the voltage and current phasors at one terminal of the line, then at other terminal you can calculate. Then if you know the like values of vi and vj both, then you can calculate the current flowing through the line, basically iij. That will be vi minus vj divided by z. So you can get iij. And if basically if there is no incoming current here, and let's say we have two lines here. So what is the incoming current? That is 0, right? Basically injection is 0, so that should be equal to the outgoing. And what is outgoing? It is IIJ plus IIK. So once this is known, you can calculate also IIK, that will be negative of IIJ. So in this way, if you know the voltage and current phases at a bus, then you can calculate consequently the voltage at the other terminal, current flowing through the line, and if there is no injection, you can also calculate the power flowing through the other lines. So likewise, I will say, let's say for bus 1 you are writing, so the observability constraint will be basically x1 plus, you can say any that lines, we have two lines and they are terminating at bus 2 and bus 5, so that should be greater than equal to 0. This is the observability constraint for the first bus. So if we consider bus 2 similarly, so it is be x2 plus, what are the lines that are, you can say, originating from this bus 2? We have bus line 2 1, right? So x1 plus, we have line 2 5, so x5 plus we have line 2 4, so x4. So I was comparing for 2, so 1 5 4 is over another 2 3, so x3, that should be, sorry, greater than equal to 1. So can anyone tell me what should be the observability constraint for bus 3? Anyone?
S2, S4,
x3, then
S,
4. Sorry, can you repeat? Actually your voice is not coming quite clearly. Basically x3 3 4 and 3 2, x2. So likewise you can write, so 14 number of equations will come for like this. You will go from 1 to 14. For a 14 bus system, you will have 14 set of observability constraint. So we are writing here greater than equal to 1 means, if basically this is indicating that PMU is installed or not. So if we install a PMU at bus 3, then we can have the information at 4 and 2, or if we install at bus 4, then we can have information at 3 and 2. So this equation is basically signifying that, it's like for this group of bus, if there is PMU at any one bus, the rest of the values can be calculated for this group. So problem formation, I think I'll skip. So I was like saying, what will be if you see our objective. So we have generators at bus 1 and 2. So basically it will be C1 as a function of PG1 plus C2 as a function of PG2, and we discussed the observability constraints, right? So 14 sets of observability constraints. Then we'll also have the state estimation constraints. So I'll just write the equality constraint for, let's say, bus 1. So the what will be the injected power? It will be PG1. So here you are injecting PG1, so that will be equal to the outgoing power, that is P15 plus P12. So what will be P15 in turn? It will be delta 1 minus delta 5 by x15 plus delta 1 minus delta 2 by x12, where my variables are these deltas. This is one example of power balance. So similarly for all bus, so again 14 equations for power balance. Then we'll have two equations for the generator's limit. Then we'll have 14 equations for this delta limit at each bus, angle limit. So these set of equations, they'll form my optimal PMU problem. So using this, we found that the optimal location for PMU for bus 2, 6, 7 and 9. So if you install the devices at these four places, you can have the or you can calculate the deltas from bus 1 to bus 14 if you know the measurement at these buses. Basically, if you know delta 2, delta 6, delta 7, delta 9, you can calculate rest all deltas. So classical optimization techniques. So basically, depending upon the type of the problem, we classify these problems. So if the objective is linear and constraints and objective and constraints are linear, so we call this as a linear programming type problem. If along with this we have integer constraints, then we call a mixed integer linear programming type of problem. Similarly, if you have objective and non-linear constraints, so it will be a non-linear programming type problem. And along this, if you have additionally integer variables, it will be a MINLP, or basically binaries. So depending upon this, we have linear programming, non-linear programming, mixed integer non-linear programming, mixed integer non-linear programming. So these are the classification of this classical optimization techniques. So in the meta heuristic type, what we do, basically we take inspiration from the biological phenomenon that is going in the world. So like we have genetic algorithm where we take the inspiration from the genes, like how the genes are being transferred to the next generation, and the survival of the fittest takes place. So that is happening biologically. Taking information from that, this algorithm is formed. Similarly, particle swarm optimization, where this is taken inspiration from a group of birds searching for their food. So how they are able to know that. So taking inspiration from that, this particle swarm optimization you take is formed. Basically, you have many other like gray wolf optimization, and colony. So these are all, like, the name is derived from which biological phenomenon this algorithm is inspired from. But what these algorithms have a disadvantage is they do not converge to the global optimal solution. They cannot guarantee that, but mathematical or classical optimization technique, they will guarantee a global optimal solution for linear problems basically. So here we can have local solution, plus depending upon the value of our initial guess, the solution we can change. You will get different solution each time you run these algorithms. So these are not that accurate basically. These are some of the disadvantages and advantages of these methods. Uh, so you can see, so GA is a heuristic, binary search, integer programming, BPSO means binary PSO is also heuristic. This is also heuristic, integer programming is classical. So these are some advantages and disadvantages that are for these methods. Then coming to the next module, basically next module, it was for the cyber physical system. So basically it is the interaction between two layers. This is the physical layer containing of physical devices or physical, you can say, infrastructure, basically your lines, your actuate sensors that are in the field. Then there are different actuators which are acting according to the control actions. So these are all my physical devices that are present in the field, and these, you can say, these are the power flows which are actually flowing in the lines. And due to the smart grid, we are additionally having this communication layer. So these are the equivalent nodes, you can say, in the communication cloud, and these are the information flows basically. So this interaction between these two systems, cyber and physical systems, is known as cyber physical systems. So any attack on the system will also affect the physical layer. So here you can see basically the physical entities. We have generators, we have then transformers, transmission lines, then distribution transformers, then we have the consumers. So basically during this, what we do, this information from this is flowing through the communication network. Basically this can be wired, wireless, or anything, and again through this it is reaching to the control center. In the control center, basically with the help of SCADA, then different studies are taken place at the control center using this data from the physical entities such as energy management, AGC, load frequency control. So these studies are carried out, and the control signal is given back through the communication layer to this physical layer. And according to this control signals, these actuators will act in the physical layer. So if this information is that is being passed to the control system, there is an attack here, then they will not get the accurate data. So they will, this study that they will do, they will be not efficient because they are done utilizing the false data, and hence the control signal they will give, that will be also not optimal for the system. But the physical layer, it is not aware of this. Any control signal it will receive, it will act accordingly. So any false control action can lead to, we can say, outage in this physical layer. So these are some advantages and disadvantages of this cyber physical systems. Advantages is basically it is leading to automation, grid automation, and we are also able to derive various smart features. It is leading to the coordinated and flexible operation of the power system, and there is two-way information power flow, and there is efficient operation of the system. But coming to the disadvantage, the malicious control effects, which I discussed in the previous one, it may happen. There may be network congestion because of flowing of excessive amount of data or information. There may be communication latencies, basically the uh, drop or the if the information that is not being passed at the right time, there may be some lag or delay in this process, so that is latency. So if there is a delay in the information received, that may hamper the control that we are getting. And lastly, cyber attacks. Basically, if there is attack in the communication system, it will hamper our physical system. So here they are divided into two types, basically false data injection attacks and denial of service. So what happens in this false data injection and denial of service, we'll see. But this false data injection attacks can happen through this sensors, like the data from that you are getting from the sensor. They can manipulate those data or the controllers or the communication links. So at these places, they can inject external data or false data to manipulate the communication that will be received by the control center. Denial of service attack, it is of two types: MITM, man in the middle attack, and suspend communication. We'll see this in the next slide. So what happens in the false data injection attack is the attacker will inject or alter the data within the system with the intent to compromise the integrity of the data for the operation of the targeted system. Basically, this is our power system. So they will try to inject some data to manipulate or such a data which can hamper the operation of our power system. So the target system is here our control center. So these control center, they are relying the data from the sensors, right? And if this sensor, if this data is manipulated, that is we are getting from the sensor, then the command or the studies that will be taking place in the control center may be inaccurate. So they will, what they will do from the sensor data, they will collect the sensor data and transmit it to the control center. So additionally, let's say some information I is flowing, so they will change it with some delta I to manipulate this. So attack injection, this is the attack injection that we are talking about. It will inject a false data in the sensor data system. So this was the sensor data, false data has been injected. So what it will do, it will can lead to misleading control actions, it may lead to equipment damages, it will risk the safety, process disruption happens, there may be like delays. Then coming to denial of service. So in this denial of service, the what the attacker wants to do is it wants to disrupt the normal functioning of the system or the service or the network by like injecting or injecting with a large amount of data in the system. So what it wants to do is that it wants that the communication is stopped. Basically, it wants to hamper this communication system. So the goal of this attack is that the network is unavailable to the users, and it wants to cause service interruptions and downtime. Basically, it wants that the communication is lost, and this is done by injecting the communication network with uh, information overload. Basically, we can say they will overload the communication network so that in turn the communication network is completely disrupted or lost. So this is basically overwhelming traffic. They will send excessive volume of traffic, data, request, and all, so that the system resources such as its bandwidth and its processing power and memory it reaches to such a point that it can no longer function. It will become unresponsive. So it can lead to, we can see, service disruptions, unavailability of the website, business losses. So you must have recently also heard about like this Facebook and all. So they are having some downtime. So in that they are losing crores of rupees also. One such type of denial of service attack is the man in the middle attack. So what is happening here? So we have, let's say, the sensor here, and the sensor is sending data to the control center through the communication link, right? And this is bidirectional. So the attacker intercept or eavesdrops the communication between them. So the attacker will sit in the middle of both these parties and it will listen to their communication. And then what it will do, it will manipulate this data that is flowing from the sensor to the control center or control center to the sensor. So the attacker will manipulate this data that is being sent. So basically first is the interception. So the attacker will position between both the parties. It is, so basically for that reason it is known as man in the middle type. And then it will monitor. So once the attacker has reached, like intercepted between both the parties, it will try to listen to their conversations basically from the data packets or messages or information. It will monitor this. Once it starts to monitor, it will then capture the information from here and then modify this data. Basically it will take data from here and it will modify and give it to the control center. So the control center will feel as if this data is coming from the sensor, but here in the middle the attack has taken place. So this can be bidirectional also. So unidirectional or bidirectional. So the attack can be from sensor to control center or control center to the sensor. Then a cyber anomaly detection approaches. So how we are detecting these cyber attacks? So it can be centralized or it can be distributed. So the centralized can be knowledge-based methods or data-driven methods. So these are the knowledge-based methods: state estimation, chi-square technique, residual-based binary hypothesis, and this is the machine learning-based or data-driven based. And in the distributed method, these are that are robust not only to the disturbance and measurement noises, but also they are robust against the incomplete measurements basically. So here we are having singular value decomposition or the centralized methods with some approximation and observer based techniques. Then in the next module we show about virtual inertia. So what we are like initially in the conventional power system we had synchronous generators. So these synchronous generators, they were heavy machineries, right? So they were having rotating parts due to which they could have the kinetic energy stored in this heavy rotating parts. But in a renewable rich power system where we are moving to wind or PV type generators, that is inverter based generators, they do not have any rotating part. So they are not able to have that stored kinetic energy, or they do not have the sufficient inertia to support the system in case of disturbance. There it had inertia. So in case there is some delta P load change or any delta P is there. So if we know if there is a mismatch in delta, our frequency is going to be affected. So what type of control actions we take? In the first level, first in the within cycles of this change in load, the inertia will act. Basically, the stored kinetic energy that will be utilized. Then after that, the primary frequency control will start within seconds. So basically, this will be through the governor valves. Like you can open or close according to this delta PL. That will be the primary frequency control and its time scale is in seconds. Then we have the secondary frequency control, basically, which is the AGC, where we are like controlling it by like this tie line power, right? Between two areas, we can provide this secondary frequency control. And in the tertiary frequency control, basically, it is happening, you can say day ahead or hour ahead. So we know we are having some spinning reserve in our system, right? What is spinning reserve basically? So this means the generators are on, because we know generators will require some startup time. So generators are on and they are reserving their power for any disturbance. They are reserving this power. They are not producing it. So that any disturbance happens, so they do not have to wait for the generators to start again. They are already spinning, we can say, or we can say these are already synchronized with the grid. Any contingency is happening, they can help in this spinning reserve. We can activate this spinning reserve to take care of the frequency, so that the time is not wasted in starting the generators and synchronizing it to the grid. So for that we are using this term as spinning reserve. So through that we can have the tertiary frequency control, and its operation can be in the hours. It is procured day ahead, but the control action will be in hours. So what we are trying to do is, with this virtual inertia, is we are trying that this renewable energy resources, they will behave according to the characteristics of the synchronous generator only. So some manipulation will do. So this renewable energy resources with some Powertronic devices and control algorithms, so that their behavior is similar to our thermal or synchronous generators, and that is termed as virtual inertia. So for that we need to store the energy for inertia, right? And this stored energy is stored in the form of the DC link of the power converters. So we store the energy in these power converters, and they are injected into the AC side according to this control algorithm that you have fed. So that way you can provide the inertia support. Then moving to the demand side management strategies we had. So we had different management strategies. Basically, first we had this peak clipping. So if you consider here, so what we are doing here, we are first going for this. So this is peak clipping. Valley filling is we will shift this load to these valleys. We'll transfer the load to the regions where we have less amount of power. Load shifting means we will transfer this load. We are not curtailing here. what we'll do, we'll transfer this load to other hours, to hours of non-peak hours basically. Then conservation and load growth, basically what it is happening here. Let's say this is your true, then in conservation the you will decrease the load, so this will be conservation, and load growth, you will increase the load to match the generation. So this is growth. And flexible loads are those kind of loads which can operate flexibly according to the need of the grid. So basically, if there is higher demand or peak demand, these flexible loads, they can decrease their consumptions, and in case of low demand they can increase the consumption, like according to the need of the grid they can operate flexibly. So for this demand side management, what can be our objectives? First is obviously maximizing the renewable energy resources or green resources, or we can also have minimize the load. Two objectives you can have: maximize the generation or reduce the peak load, minimize the peak load. Then we have maximizing the economic benefit, basically economic benefit or social welfare. So social welfare is computed basically as the revenue that is generated, revenue generated minus the cost. So this is the social welfare. So always we will try to maximize this. And lastly, we will also try to minimize the power imported from the distribution grid. So basically, we'll be having PVs here. So this power that is flowing from the distribution system to this, we can say microgrid, we can minimize this power so that energy can be produced and consumed locally. And when it is done that way, the losses will be decreased, and the like you need to pay for the power that you import from the grid, right? So the we can say payment to the grid will decrease so that profit can be maximized. Then this demand side management, it can happen as single objective or multi objective. So what do we mean by a single objective and multi objective? Can anyone like to say? Anyone? Why are we going for this multi objective type function?
Minimize, maximize, then
Like if you want to minimize something and conversely you want to maximize something. But why this disparity will come in the first place? Because we are having
minimizing loss and maximizing the profit.
hmm, so then why we need to go for like multi-objective. So if we have two players or two entities who have contrasting needs or contrasting objectives, then to like look after the objective of both the players, we need to consider a multi-objective. But even if you have two players and their objectives are aligned, like if they both want to have the same objective, then we can go for single objective. But if these two players, they want different, they have different needs, they have different objectives, they have different, you can say, expectations, then we need to have multi-objective function so that we can strike a balance between those two players. Because let's say some player wants that PG should be 5, the other player profit is when PG is 10, the same PG1. So if you go for single objective, for player 1 you'll get 5. In that case, player 2 will get heavy loss. And if you optimize in the according to player 2, then player 1 will have heavy loss. But if you consider their objectives in a multi-objective function, then their total, you can say, dissatisfaction will be reduced, because here we are considering both of them. So maybe the multi-objective will give some solution 7.5. So now also they are facing some losses, but it will be less than what they would have got in case of single objective. So for that, when we want to strike a balance between two contrasting objectives, we are going for multi-objective functions. So actually I had a problem here for like example. So let's say you have a 3-bus system with 2 generators. Mm, So, and we have a load here of, let's say, 10 megawatt, and let's say the price or the cost, basically not price, the cost of production here is rupees 3 per megawatt, and here it is rupees 2 per megawatt. So if you carry a simple economic dispatch, so what will be the solution basically here? Which generator will be dispatched? The cheaper generator will dispatch. Basically, the solution will be that this generator will be producing 10 megawatt power. This generator will be not dispatched. It will be producing, or it will have 0 megawatt of power. But in in combination to the cost function, we also need to take into account to the losses that are going to the system. So let's say, and the losses will in turn depend upon the line resistance here, right? The resistance of these lines. So let's say you are generating 10 megawatt of power here, but these are extremely lossy lines. So let's say 2 megawatt of power is lost here. So finally what you get here is 8 megawatt of power. But again here, even if it is costly, let's say if it is connected to a line which is less lossy, and you will inject your 10 megawatt of power, maybe you will get 9.5. So how to strike a balance between this cost minimization and loss minimization? So that is here the contrasting objective. So let's say this R is 0.8 here, and here it is 0.2. And let me say that my objective is minimize W1 times, first I have cost minimization, so 2 times P1 plus 3 times P2, plus my next objective is for loss minimization. So it is W2 times, this is 0.8 times P1. Basically this P1 is equal to P12 plus 0.2 times P2. So depending upon this W1 and W2, we'll get different solution. Basically, if you set W1 greater than W2, that means you are focusing more on cost minimization. If W2 is greater than W1, then you are focusing on loss minimization. So let's say for W1 equal to 1 and W2 equal to 0. So in this case, what will be P1 and P2? Basically, this is 0. That means you are only having cost minimization. So for cost minimization, what will be the result? You said it in the first, right? W1 is 1, W2 is 0. So we are having only this part. That means P1 will be 10, P2 will be 0. Is this clear, sir?
Yes.
Let's say then we take W1 as 0.8 and W2 as 0.2. So now my objective is, this is 0.8, this is 0.2. So we have two options. Either P1 is 10, P2 is 0, or P1 is 0 and P2 is 10. Right. So under such condition, what will be the objective function? It will be 0.8 into 2 into 10 plus this is 0 because P2 is 0 plus W2 times, W2 is 0.2, 2 times 0.8 into 10, and again P2 is 0. So what will this give me? So basically this will be 2 into 8, 16 plus 8 into 0.2, 1.6. This will be 17.6. And if we consider this one, what will be our objective? It will be 0.8 into 3 because P2 is non-zero here, and 10 plus 0.2 into 0.2, because now this line is power flowing, into 10. That will give me 24 plus 10 to 0.4, so 24.4. So what is the minimum between these two? This is 17.6. So this will be my optimal when W1 is 0.8 and W2 is 0.2. But again, if you consider W1 as 0 and W2 as 1, so what will be the solution? Can you guess? So our objective will be basically this one, right? 0.8 times P1 plus 0.2 times P2. So if P1 is 10 and P2 is 0, so the objective will be 0.8 into 10, which is 8. And if P1 is 0 and P2 is 10, so it will be 0.2 into 10, so it will be 2. So this is the minimum and this is my solution in case of this W. So you can see the solution is different. Here P1 was 10, P2 is 0 when we have the W1 as 0.8 and W2 as 0.2. But when we change this to 0 and 1, we get that P2 is 10 and P1 is 0. So depending, what I wanted to convey is basically depending upon this weight W1 and W2, the solution will be different. So it is like which objective you want to prioritize more. So that way you need to tune the parameters of this objective W1 and W2. So I hope this was clear. Suman ma'am, okay, are you there? Then coming to demand response. So these are some of the objectives that we can take for demand response activities. So it can be minimization of cost, maximization of welfare. Minimization of this aggregator is basically, you can say, a private player. So minimizing its power or minimization of both this cost and power consumption, this multi-objective, or maximization of social welfare and minimization of this aggregator's power consumption. So coming to various demand response programs, so it can be classified first based on control strategy, whether it is a centralized or a decentralized one. So what will happen in centralized is the, you can say, DSO will give the dispatch for the demands, for demand command, dispatch commands. And for decentralized control, the DSO, what it will do, either it can happen like there is a DSO, there is a aggregator, and there are loads. So the aggregator can act between these two quantities. So in that way, it can be decentralized. Then, depending upon price. So dynamic price-based demand responses basically, instead of giving a flat price to the customers, what it can do, it can generate a time varying price. This price can be time varying, so that in the time of high demand it can send high price, so that the price consumption can be decreased from the demand response, and in case of low demand period it can give lower price. So the objective will be to basically flatten the load curve, because when we are having this type of load curves with peaks, so it will lead to inefficient utilization of the resources. The utilization factor here will be very less, because to meet this peak demand we have to assign some resources for very small amount of time, and for the rest of the time they will be idle, so their utilization factor will be very less. Then coming to dynamic prices, then next is incentive or penalty based demand response. Basically, according to the need of the grid, if the demand response are acting, then it can provide some incentives, and if it is acting opposite to the need of the grid at that time, then it can impose some additional penalty. And these dynamic prices, they can be of different type. Basically, critical peak pricing, that is in the time of high load, the price will be higher. Similarly, peak load pricing, real time pricing, not in the day ahead, if the prices are given for the real time. Then time of use tariff, basically for this time varying here. So depending upon what time of the day you are using, the price will be varied that way. Then based on load, it is either task related or energy related. So in the task related, what you are doing here is the you have E, you have time, and you have energy or power basically, or energy. So the time, the consumption time, let's say it wanted to use between T1 to T2, and it wanted to use in this way, let's say. But in task related demand response, the time will be fixed, but no, the in task related, what will be doing that, the time will be varied. Basically, in the new demand response activities, it will reduce its consumption times, but the profile will remain same. The energy profile will remain same. But in case of energy related DR, the time will be kept constant, but the profile of power or energy, that will be changed. So basically the time will remain fixed, but this profile, it may be changed. So coming to the question and answer session, so which type of variables are used in optimal PMU placement problem? Binary, integer, continuous, binary and continuous.
Continuous.
Binary and continuous. Suman ma'am, would you like to? take a shot here. So here in the problem, in the optimal PMO placement, we discussed there was binary variable X, but there are also continuous variables like PG, there was PIJ, there was delta IJ, delta I. So these are continuous, and the decision whether the PMU to be installed or not, that was binary. So the correct answer is binary and continuous. Then a sensor attack falls under which category? False data injection, man in the middle, denial of service, distributed denial of service. Sorry, sir, once again. Or you may type. Actually, your voice is. If you may type, then it will be nice. False data injection. True. So here, basically, in the sensors or in the actuators, externally, we are injecting some data. Why cyber anomaly detection methods are needed? For continued normal operation of the system, to isolate the faulty or the compromised part, for increasing the cyber resiliency, or all of the above. Yeah, so with this detection techniques we need for all of these advantages that we will get for. So basically these two will in turn lead to increased cyber resiliency in case of an attack has happened. So how quickly we can isolate the compromised part and restore service to the healthy part or the non-attacked part, that will lead to increased cyber resiliency. So all of the above. Which sources can provide inertia? DFIG, energy storage system, synchronous generator, all of the above. So here we can store the energy, here also. This was also there. So the correct answer is all of the above. Then what ancillary service the virtual synchronous generator cannot provide? Inertia, primary frequency control, voltage support, or none of the above. Beware, it is can't provide. Voltage support, actually VSG can also provide voltage support. So basically it can provide all these ancillary services. So the answer is none of the above. Then which demand side management strategy is more reliable compared to other? Load growth, peak clipping, flexible load, or load shifting? Anyone? This is basically load shedding, which is always not desirable. Then load growth. So this answer D. Load growth, it is always not possible, or it cannot happen in a very short instance of time that the load will vary or it will grow. Flexible load, again, it is not that reliable because the loads, they won't like compromise on their consumption, but load shifting can always happen. They can consume that same amount of power but during different time intervals. So this is more reliable load shifting. Then which of this demand side management strategy is used in DC microgrid to reduce peak demand in AC system? So basically loads are of two types, B, peak clipping. So they are of DC and AC. So using the DC microgrid, if this DC loads can be met, then the amount of AC load or the total load in the system, it can decrease because we are supplying the power locally. So it is not, we are not shedding any load here. So it is basically shifting of loads. So shifting from the distribution system to the DC microgrid basically. The load profile of which type of consumers are confidential? Residential, commercial, industrial, all of the above. Residential, but are residential consumers very much interested for their load consumption pattern? Like consumers such as we, are we, do we care if anyone is monitoring what is our load pattern throughout the day, what amount of power we are taking? So this is not very significant because not much can be derived from this data. But coming to industrial, if their load profile is disclosed, then it can be like they can be, then it can be hampered because let's say certain company, your rival companies is able to know that your peak power consumption is during certain time of the day. So let's say this delta t. So it may then guess more amount of power means,
Madam, the answer is A only.
like can you discuss like why you think residential consumers are?
Because residential, if you are connected with what you say, power, what you say, panels and all.
Huh.
So your generation and your consumption will be a threat to you also because suppose if you are not consuming, somebody may think that you are not in your home and all. So that is why residential is more confidential. It is related to the privacy of the individual.
Huh. That thing can be in case of some like thief or those kind of burglary can happen They can break into your house if they study that during certain.
Industry, industry has to take power from the government utility, so
Hmm.
they can very well disclose that when their peak is there. Because if they will not disclose, then the grid operation may hamper.
No, one second. If they what government part I couldn't get.
So they have to disclose what is their peak. Otherwise, grid stability will be in the question.
Huh. So confidential means what we are saying that who are more like unlikely to share their data with others, right? So residential, this part is obviously to some angle makes sense that if some third party is monitoring your house, so let's say during certain period your power consumption is zero near about, it can then think that at that time no one in this is there in the house, and it may then like carry the thief, the it may attack during those period of time. But this is not, I can say, directly shared with a government or the distribution company, which will not like disclose this data to the common people, right? We are here like talking about the industrial consumers. This will make sense for both this up to some level, but for industrial it will be very very confidential, because then it will hamper their profits. What I was trying to say, like if the certain industry is consuming power during certain period of time, then the rival may think or it may guess that which like they are having different units, right? In which unit they are running. Basically certain we are having player industry A and industry B, and industry B is having greater profit, and profit is greater here. So the industry B will like to know what strategy the industry is following, so that it may also increase its profit. So this strategy it can guess by looking to its load profile. Let's say the increase, the change, previously the industry had a load profile as this way, but now the load profile has changed. So from that it may guess that which unit the industry A has changed, and accordingly the industry B can change that unit to increase its profit. So large industrial consumers, so for them it is very very confidential. So here you can say industrial is the correct answer, but if you go to very deep in the case, then maybe uh, not now, and it may not be relevant to now, but let's say the smart meters and apps that may come up in the future. In those cases we can say all the consumers, they will be aware, they will become they will not like disclose any of their information. Then demand response program applied on residential consumers are specially named as home energy management system, house energy management system, residential energy management system, or consumer energy management system. Consumer energy management system. Actually, it was in the slide only. To name it, we can name anything, but that special term that has been given is basically home energy management system. So here basically your refrigerators, washing machines, ACs, we can say heaters, thermostatic loads basically. So these take part in the demand response activities. So any doubt for this week? Anyone? Okay. If no doubts, I think then we'll close this session for today. Thank you everyone for joining. We'll meet in the next week to discuss the content for week 9. Thank you, sir.